Hey everyone, and welcome to this explainer. I am absolutely thrilled you're here because today we're taking a structured deep dive right into the super fascinating world of bitwise manipulation. We're going to look under the hood of a computer to see exactly how a processor performs hardware-level math and logic. If you've ever wondered how a machine calculates things literally at lightning speed, or how it filters data at the absolute most fundamental binary level, you are in exactly the right place. We're going to unpack all of this, breaking down some pretty complex concepts into simple, visual steps. So let's get into it. Okay, let's take a quick look at our roadmap. First up, shifts for multiplying and dividing. Then, bitwise masks for extracting and setting. After that, toggling bits with XOR. We'll ground this in the real world by looking at IP addresses, hit a quick quiz on logical operators to lock it in, and wrap up with an exam prep summary. All right, section 1, shifts, multiplying and dividing. So I want to start by posing a really fundamental problem. We humans memorize multiplication tables, but how does a computer actually multiply numbers at the raw hardware level? It doesn't sit there referencing some internal mental chart. Instead, it relies on an incredibly elegant, simple solution, binary shifts. By literally just moving zeros and ones left or right, it can perform instant arithmetic. Let's look at a binary left shift in action. In step 1, we start with the binary sequence for the number 22. Now step 2, imagine physically pushing every single bit one position over to the left. The bit on the far left edge, it just falls off and disappears. But what about the newly created empty slot on the far right? Well, we simply pad it or fill it with a 0. Step 3, if we read this new binary sequence, the number is now 44. It's like magic. In effect, by doing a single left shift, we've just multiplied our original number by 2. And hey, if we shifted it 2 places, we'd multiply it by 4. Now, what if we go the other way? A binary right shift does the exact opposite. Step 1, we take our sequence. Step 2, we shift all the bits to the right. The bit on the far right edge falls off this time, and we pad that empty space on the far left with a 0. And the result in step 3, we've exactly halved the number. We successfully divided by 2. Literally just by sliding the bits over. Okay, so here's a super crucial distinction, especially if you're taking a computer science exam. The shifts we just looked at, the ones that always pad the empty space with a 0, those are called logical shifts, and they work perfectly for unsigned positive binary numbers. But think about 2's complement signed binary for a second, where that leftmost bit, the most significant bit, is a signed bit. A 0 means positive, a 1 means negative. If you perform a logical right shift on a negative number and pull a 0 into that leftmost slot, you suddenly turn a negative number positive. That completely breaks the math. So to safely divide negative numbers, we use an arithmetic right shift. Instead of padding with a 0, an arithmetic shift fills that vacant spot with whatever value was previously held in that most significant bit. It perfectly retains the negative sign. Moving on to section 2, bitwise masks, extracting and setting. So what exactly is a bitwise mask? Well, think of it kind of like a physical stencil you place over a piece of paper. The stencil has holes cut out to let you see or paint certain areas while completely blocking out the rest. In computing, a mask is a binary sequence used alongside logical operators like AND, OR, and XOR to selectively isolate, extract, set, or toggle specific bit values in another binary sequence. And this right here brilliantly illustrates how an AND mask actually extracts data. We've got our original sequence, and below it, an AND mask made of 4 1s and 4 0s. When we apply a bitwise AND, both inputs must be 1 for the output to be 1. Look at what happens. In all instances where the mask is a 1, we effectively just copy the original binary sequence straight down to the output. But where the mask is 0, we are totally blanking out or ignoring the original sequence, forcing the output to 0. Right here, our mask has cleanly extracted just the first nibble, the first 4 bits of our original data. Now let's contrast that with an OR mask. Here, we're doing a bitwise OR operation. With OR, only one of the inputs has to be a 1 for the output to be 1. So check out the first 4 bits where our mask has 1s. The output for that whole first nibble is set to 1, regardless of what the original sequence was. An OR mask is perfectly designed for setting bits. Where you put a 1 in the mask, you force the output to 1. Where you put a 0 in the mask, you just leave the original sequence exactly as it was. All right, section 3, toggling bits with XOR. So this is XOR, which stands for exclusive OR. The rules here are pretty strict. The output is 1 only if one input or the other is 1. If both are 0, the output is 0. But crucially, and this is the exclusive part, if both inputs are 1, the output is also 0. It is strictly exclusive. Let's see it in action. We're applying an XOR mask of 4 1s and 4 zeros here. Where the mask is a 0, on the right side, the original data is just left completely alone. But look at the left side, where the mask is a 1. Because of the exclusive nature of XOR, a 1 matching with a 1 results in a 0, and a 0 matching with a 1 results in a 1. So what effect has this actually had? The bits have been perfectly toggled or switched around. The 1s became 0s and the 0s became 1s wherever the mask had a 1. XOR is literally the ultimate toggling tool. Section 4. The real world. IP addresses. Okay, let's ground all this abstract math in a real-world networking application. Every single computing device uses an IP address to route traffic across the internet. Now, you're probably used to seeing IPv4 addresses as a set of 4 decimal numbers separated by dots. But under the hood, computers definitely don't store them that way. That decimal format is really just for our human convenience. Computers store each IP address as a raw 32-bit binary sequence. And importantly, that sequence is broken into 2 distinct parts, a part that identifies the network and a part that identifies the specific host device on that network. So when a router needs to figure out where to send traffic, it has to isolate that network ID to see if the destination computer is actually on the same local network. How does it do that? It uses a bitwise AND mask by taking the 32-bit IP address and applying a specific subnet mask. Using the AND operation, it perfectly blanks out the host information and extracts just the isolated network ID. This literal mathematical operation happens millions of times a second across the globe just to keep the internet running. Section 5. Time for a quick quiz on logical operators. All right, let's test your understanding with a rapid-fire quiz to really lock this in. Here's your first challenge. What is the logical result of 1 or 1? Think back to the rule for the OR operator we covered just a minute ago. And the answer is 1. With an OR operation, only one of the inputs needs to be a 1 for the output to be a 1. Since both are 1s here, the condition is more than met. This is exactly why OR is so perfect for setting bits to 1. Okay, next question. What's the result of 1 XOR 1? This is the tricky one that frequently trips up students on exams, so take a second to recall the strict definition of XOR. The answer is 0, because they're both turned on, and XOR stands for exclusive OR. A double positive results in a 0. Remember, XOR is strictly exclusive, making it the perfect tool for toggling bits. Finally, Section 6, Exam Prep Summary. Let's summarize the absolute highest yield facts so you're ready for any test. Remember, a binary left shift multiplies by 2, and a binary right shift divides by 2. Now, a really important note for those of you taking the OCR exam, the clarification document actually states you only need to be able to perform right and left logical shifts. That means arithmetic shifts shouldn't even come up on your test. Moving on to masks, remember our catchphrases. AND extracts data, OR sets data to 1, XOR toggles data. And finally, all of this is used in the real world to do incredibly important things, like isolating network IDs and IP addresses for internet routing. So we've thoroughly explored shifts and masks today, unlocking a core piece of how computers actually think at the hardware level. But this is really just the beginning. I want to leave you with this final provocative thought to spark your curiosity. Beyond shifts and masks, what other operations do you think a processor's arithmetic logic unit carries out to make our modern digital world possible? Keep exploring, keep learning, and thank you so much for joining me for this explainer.